Hello and welcome to the 8th session of Maths and Ideas with Reza Negrestani. I'm going to pass the mic off to him now.
Thanks. Okay, so let's start today's session. I'm going to briefly talk about a very, I think, important, at least from a historical point of view, rather than kind of a philosophy of mathematics perspective, relation between mechanics, machines, engineering, and mathematics of late antiquity to late scholastic era. And why is that we need to pay attention to this relation between machine engineering and the hegemony of geometrical analysis throughout this time period. After that, after this brief excursion, I'm going to talk about the work of Nicole Orim, inductively the most important natural philosopher of Middle Ages. He was an archbishop, an astronomer, economist, mathematician, logician, philosopher. I'm going to talk about a little bit about his invention of mathematical graph and how he, which, as I will explain, the invention of mathematical graph has something to do with this relation between analogic geometry and mechanical engineering, namely the relation between the mechanical analog and the geometrical model. And given the fact that historians of science now completely agree that Galileo's and Kepler's formula for motion of celestial bodies were not utterly revolutionary, but simply modifications of Orim's formula of mean speed and acceleration. That makes Orim's contribution, that I will talk about, even more compelling from a historical perspective. The reason, aside from Orim being, the most important natural philosopher and logician or mathematician of the Middle Ages, the reason that I've decided to talk about Orim's contribution is because I think Orim consolidates some of the most important observations about the relations between mathematics and physics in the Middle Ages that led to the so-called Copernican revolution and ultimately conditioned what you might call to be the modern framework for natural sciences, whatever we know as science at this point. So before starting our course, is there any question about the previous sessions, about particularly the last session we were talking about Euclid's system and the internal configuration of Euclidean diagrams?
Yeah, I posted a question in the classroom after after reading the Stegmuller text that you recommended, or I just read the chapter 2 about the axiomatization of a theory. And I was just wondering if it's not too much of a side conversation, if we could talk a little bit more about the role that intuition is playing. And then the more basic question that I have is, how do we separate the constructive role of the that postulates and definitions play from the relational role that axiomatics play? They're just sort of really broad questions. If it's too distracting right now, then maybe it can happen in the classroom.
Okay, just very quickly, remind me. I read a Stegmuller's text a long time ago. Remind me what is exactly the difference between the constructive approach and the relational approach, or the relational role.
That's, he only mentions that really briefly. Let me just pull it up really quick.
Is this from his book on theoreticity?
This is from, yeah, the structure and dynamics of theories. Is that?
Yes, yes.
Yeah, and then it's in chapter 2 on axiomatic theories. I'll just read sort of slowly this one paragraph. Because we are for the moment concerned only with drawing a comparison with the Hilbertian notion of an axiom system, we could just as well have spoken of the concept of an axiomatic system in the Aristotelian sense. Historically, though, various differentiations would have to be made that, for the most part, remain neglected in philosophical discussions of this topic. Existential quantification, for instance, plays a different role for Euclid than it does for Aristotle. Furthermore, axioms in the strict sense, relational sentences, would have been distinguished from postulates, construction sentences, an undertaking which presented considerable difficulties even in ancient times. For a very penetrating and concise discussion of these, and then he lists a place to go look. Underlying the evidence postulate, according to which the truth of all axioms must be directly apprehensible, is the idea that fundamental notions employed in the axioms be derived from intuition, so that the evidence takes on the form of an insight emanating from these notions.
Okay, I think I mentioned this a couple of times, that I know that people like Lawrence Pontel, and by the way, you absolutely have to read Lawrence Pontel book Structure and Being if you are interested in this whole idea of what really philosophy is and should be, and what is the relation between philosophy and sciences at this point. I highly recommend Lawrence Pontel's Structure and Being. One of the things that is important here to mention is that even though I think people like Stegmuller and Pontel talk about Euclid's definitions as an intuitive axiomatic system, I really do not think that Euclid's definitions are axioms, even in the intuitive sense. But let's believe that they are axioms in the Stegmullerian sense, that they are derived from intuition, the Kantian sense. I think so. There is I think even so, from an intuitive Kantian intuitive perspective, Euclidean's definitions can be dealt with as what you might call to be rudimentary axioms. The difference between Euclidean systems and Euclidean axioms and Hilbertian axioms is that it's something quite specific, actually, in the sense that, so this is really a Stegmuller's insight, that when you have intuitive axioms in the Euclidean sense, with limits of perceptual systems rather than limits of language or logic, is that the intuitive, the kind of system that you can build on these axioms is going to be a one model system. Whereas Hilbertian definition of axiomatic systems allow you to interpret n models, namely cohesively finite, and this finite means any large amount of models within your given axiomatic systems. So, and why is that? It's precisely because Hilbertian system is about this, what you might call to be macro-theoretical relation between the statements of your theory. You can think of this as statements regarding your postulates. They have been couched in terms of, or in the vocabulary of natural language, but also in terms of the relationships between, and these relationships are not just any form of relationships, they're logical relationships between your axioms that can be couched in set theoretic terms. Now, Hilbert's picture of an axiomatic systems allow you to derive multiple models from one axiomatic system. Not because it completely abstracts away from the intuitive import of your so-called axioms, but precisely because it sees an axiomatic systems across different scales, in the sense of some formal, in sense of intuitive import of axioms, namely your self-evident building blocks of a theory. Then the relationships between these intuitive axioms, which are usually logical, and then at a higher level, in terms of what you can construct, the model that you can construct out of these logical relationships. So from this perspective, I think Hilbertian understanding of an axiomatic systems, particularly with regard to the Euclidean system, is not by any means a form of rigidification, as if you think that, oh, precisely because of Hilbert's school of formalism, he's basically proposing some sort of complete break away from the intuitive imports of Euclidean axiomatic system. No, that's really actually that couldn't be far from the truth. In fact, even though Hilbert goes for the formalist approach, namely trying to talk about an axiomatic system in terms of logical relationships between your axioms that allow you to build different models, he basically, from a certain perspective, is arguing that even though Euclid systems is a completely intuitive systems in terms of its axioms or definitions, if you manage to de-stratify if you manage to hierarchize basically study the system along different scales, the axioms, the postulates, the constructions, the proofs, so on and so forth, logically in terms of logical connections or relations, then you are capable of, in fact, developing different models out of a Euclidean system. And some of these models might not be even compatible. So this is, I think, a really an interesting insight that simply by allowing a hierarchical view from a logical standpoint of Euclidean system and how what axioms are and how they stand in relation to one another, and how by virtue of these relations they afford certain constructions, Hilbert argues that if we take the idea of Euclidean system beyond its intuitive givens, then we are capable of, in fact, developing different models from a base Euclidean system. What we know that the Euclidean system, at least in its traditional framework, what you might call to be one axiomatic theoretical systems and one model only, that they stand in one-to-one relation to one another. Hilbert instead argues through the moving toward an abstract axiomatic system couched in theoretic terms, you can multiply this. That even though you have one axiomatic systems, you can nevertheless have different mathematical models out of the systems that can or might be even incommensurable, might be completely different from one another.
And when you say hierarchize, you mean hierarchize in terms of fundamentality, is that?
More in the sense of the relations between what you might call to be your intuitive definitions, your common notions, your postulates, and your theorems. That they should not be bunched together according to the same intuitive principles.
Right.
The intuitive principles only hold for your very base axiomatic vocabularies, namely, for example, what a line is, what a point is, so on and so forth. There is no reason to extend these intuitive relations between your base definitions to higher levels of constructions, namely postulate, theorems, so on and so forth.
Looks like Maria types a question. Do you want to say that, Maria, out loud?
Oh, I guess I just Googled Hilbert.
Maria always asks difficult questions, by the way.
I don't know.
Yes, I love it. Okay, go on.
Yeah, I'm interested in like how spatially, because like how you would think about this spatially, because Euclid's system is like you're talking about how it's kind of like diagrammatic reasoning. And is there like a diagrammatic, and I'm just throwing this out there, I really don't know very much about like Hilbert or space, but like is there like a diagrammatic element or analog to Hilbert?
I think the relation between the two really requires some heavy mathematical elaboration. It's not let me put it that way. Hilbert's space, at least from a philosophical mathematical perspective, has nothing to do whatsoever with the Euclidean system. Nevertheless, what is really has some relation with the Euclidean systems, it is Hilbert's understanding of mathematics, namely the role of axiomatic systems. Is a school of formalization, in the sense that what is really mathematics for Euclid is that you can have an intuitive unity at the level of axioms. And this is already in the case, in terms of Euclid systems. But the difference is that whereas in Euclid, if you have an intuitive unity, you only have one model. And that's what you might call to be conventional E-system Euclidean geometry, plane, and the stuff that we were talking about last session, that, you know, if you have basically an wrapped two-dimensional plane in which, for example, two circles that intersect, the point will be on the same plane.
Mm-hmm.
So this is a model that corresponds with the intuitive unity that stands between your axioms or base definitions. Whereas Hilbert's tries to show that if you stratify or understand this Euclidean basically philosophy of mathematics across different levels, then you can derive, in fact, multiple, if not infinite, models from the same unitary relations that stand between your axiomatic systems. That even though what you might call to be the relation between your base definitions, your intuitive axioms, are stable, you still can develop mathematical models or mathematical spaces out of these stable relations that can be fundamentally different to one another. But this can only be done if you see the relation between intuitive axioms and your proofs, namely constructions, no longer in terms of intuitive principles, but in terms of pure set theoretic principles that are couched in set theoretic terms. It's the idea that, you see, Kant also has, and I think, as I mentioned, I think Hilbert is quite Kantian in this sense. You might say that Euclidean systems demarcate the limits of imagination. And what is really imagination in Kant? It is a representational relation between what you might call to be a singular representation and an item in the environment, an object. It's a one-to-one correspondence, namely an image. This is the idea of image in Kant, a singular representation of an object. It's a one-to-one correspondence. But if you subsume, namely reappropriate, or this one-to-one parochial representational correspondence under the category of pure concepts of understanding, these are no longer images but concepts, pure concepts, then you are capable of reinterpreting this image in different guises. Imagine, like, you know, the duck rabbit. The duck rabbit is only a duck rabbit precisely because you are subsuming an image under different concepts, and you see it differently. A concept of a rabbit and a concept of a duck. Because you have already stepped outside of the rudimentary relation between the image that you perceive and the represented object. You have moved toward the realm of pure concepts, that you can see it differently. The same thing here with Euclid, with Hilbert's understanding of Euclid's system. That even though the intuitive import of Euclidean systems allows one-to-one correspondence between the system, the constructive system as such, and its definitions, well, once you diversify this relation by way of basically inscribing it in logical set theoretic terms, then you are capable of extracting different models, different conceptual mathematical systems out of one basically intuitively held axiomatic system.
Cool.
Does anyone else have any questions before we move on to? No?
Okay, so let me put the iPad on. Hopefully we have a better connection today.
Yeah, the connection seems a lot better today. So
Okay, super. Can you see the whiteboard?
yes, that's
Good. So very briefly, from a historical perspective, the first person who talks about this implicit connection between mechanics as embodied in mechanical engineering, namely invention of machines, and mathematical structures as embodied at that time in analytic geometry is Archimedes. This is the so-called method, the method, namely making explicit the relationship between mechanics and mathematics. Is it possible, if we are encountering a mathematical model, to step outside of the mathematical structure, enter the realm of physics, particularly mechanics, and search for a solution to that mathematical problem in a machine? Can a machine, a mechanical machine to be precise, solve our mathematical problem? This is really the so-called Archimedean method, which is based on this assumption that Archimedes' approach of applying mechanical thought devices to geometric problems can be viewed in a more general way than he demonstrated in his famous book, The Method. In this view, a mechanical analog is constructed that can be reasoned about more intuitively than the abstract reasoning required to solve the original problem in mathematical terms. In constructing this mechanical analog, a mechanical surrogate must be chosen that relates to the original problem through a binding principle. The binding principle asserts a set of truths about the behavior of the mechanical surrogate, namely the machine, that connect the surrogate to the original problem. As a consequence, we can solve the mechanical analog as a way of arriving at the solution to our original geometric mathematical problem. This mechanical reasoning does not need to replace geometric reasoning to be effective, but rather can complement it and offer new conceptual insights. And really, this opening of this new relationship between mechanics and mathematics, between machines and mathematical abstract reasoning, is something that is fundamentally predominant in Middle Ages. That virtually the most, or important and significant contributions to mathematics and natural sciences have been done through the Middle Ages, not by abiding in the realm of mathematics or in the realm of physics, but by creating a back and forth oscillation between physical embodiment, physical, what you might call behaviors, and basically mathematical assumptions and reasoning. And this form of thought procedures, going back forwards between mathematics and physics, is embodied throughout the Middle Ages, if not from early antiquity onwards, in the relationship between the mathematician and the engineer. Mathematical reasoning and mechanical machines. I do not want to go to details about how this fertile relationship between mathematical reasoning and mechanical machines ultimately led to what you might call to be computer science at this point, but I want to focus precisely on the nature of this going back and forth, this oscillation between machines or mechanical surrogates and abstract mathematical principles. So I would like to make a diagram here and that kind of capture the spirit of this oscillation between geometric reasoning and what you might call to be mechanical reasonings, between the mechanical analog and the abstract mathematical model that allowed so many scholastic medieval philosophers solve some of the most important problems in physics and mathematics of their own era, but also, most importantly, particularly as I will talk about Urim, they allowed some of these scholastic philosophers to pave the road for a system of reasoning that paved the road for what you might call to be the advent of modern natural sciences, Copernican, Keplerian, and Newtonian revolutions. So the diagram for the relation between geometrical reasoning and mechanical reasoning can be made something like this, that you have two sides. You want to get your solutions. This is math. This is mechanical or the machine. This is equivalency. And you have your geometric problem. And you have your mechanical analog problem. there is a relationship between your problems that also can be interpreted in terms of equivalency between the mechanical analog and the geometrical problem. This is the mechanical interpretation. And this is reinterpretation. For you to get your, basically the equivalency relation between your solutions, you have here mechanical analog in order to solve it, you need to embark on mechanical reasoning. To embark on solving your geometrical problem, you partake in geometric reasoning. And this is really an overall model of how Archimedes, but so as mathematicians and engineers of late antiquity and Middle Ages, understood the relation between mathematical problems, particularly geometrical problems, and mechanical engineering problems. So you have a geometrical problem, you interpret this you interpret this according to a mechanical analog. You simply model your problem on a mechanical analog according to a principle. And then once you have that, you can go back and forth to refine the relation between the mechanical analog and the geometric problem. Once you have done that, you work on this side of your diagram. Once you refine your mechanical analog to make sure that it really does capture your geometric problem, then you go to solving your mechanical analog problem by way of mechanical reasoning. Once you arrive at a solution, then you are capable of transposing this solution to your mechanical problem as a potential solution to your mathematical geometric problem. The same also holds if you had a mechanical problem that you wanted to answer. You step outside of it, model it on geometric problem by way of this equivalency relations of interpretations and reinterpretations. You do, once you have a geometric problem that truly corresponds to your mechanical problems, then by way of refining this geometric problem, then you are capable of using geometric reasoning, arriving at a geometric solution, using the same equivalency relations and positing it as a potential solution to your mechanical problem. So this is an overall model of the correspondence between mathematics and engineering that has been extensively used since the time of Archimedes. This is, in fact, really the elaboration of the so-called Archimedean method. Before I move forward, any question? Okay, so again, the original geometric problem is reinterpreted using a mechanical analog. The analog is related to the original problem through a binding mechanical principle. using mechanical reasoning, we can then solve the analog to arrive at the solution to our original problem. This connected Archimedes' mechanical ideas with his geometric ideas. When considering, for example, the volume of a sphere, we can come up with a way of, so let's take a step back. An example of this would be, we have a cylinder and we have a sphere that is inside of it. So we have essentially two volumes. Volume, what you would call to be cylinder, volume of the sphere. Now, this is a geometric problem. How are we going to make explicit or simply elaborate about the relationship between the volume of a sphere and the volume of cylinder? How can we solve this geometric problem using a mechanical machine? Hint, by mechanical machine, I do not mean it's some sort of like a clock or something like that. At this point, what we are talking about are just simple combinatorial machines. A lever, an inclined plane, an axle, a wheel, so on and so forth. And here, again, the hint would be the kind of a mechanical machine that we want to use in order to solve this problem would be a lever, an Archimedean simple machine. How can we use a lever, a mechanical machine, to solve this problem? Elaborating the relation between volume of a sphere and volume of a cylinder. Any idea? Yes, it is quite in line with ampliative, explicative, analytic, synthetic distinction, this whole idea of mechanical engineering and mathematics. Yes. So you have a like that. So if you put a sphere inside a cylinder, then how much bigger is the cylinder than the sphere? Another way of formulating the relation between the volume of a cylinder and the sphere that it envelopes. It doesn't matter if you're coming with the right solution, but as long as that would be fantastic if you can just talk about possible solutions to this problem.
I have no idea.
Okay, so it goes like this. To answer this question, we must think about Archimedes' principle of lever, which is essentially about the idea of a balance. And it could compare the weight of two objects. If one object was twice as heavy as another, it would be balanced at half the distance to the fulcrum as the other object. Using a balance with adjustable lever arms, we can experiment, for example, with wooden blocks of different shape and sizes and adjust the lever arms to get them to balance. Now, we know that objects with shorter lever arms were heavier by that same amount. By making carefully measured, for example, clay models of a sphere and cylinder, and by adjusting the lever arms, we can guess that a cylinder is 1.5 times as bigger as the sphere that it sits inside of it. We can well, of course, in experimenting with this mechanical model, we need to make sure that we are using materials that have the same density, that are the same, in order for it to work. So it goes something like this. So imagine that we have this. This is our basically problem. A sphere within the cylinder. We make a lever. According to their volumes. Since we know, for example, the volume of a cylinder and volume of a sphere, then we have to, in order to make a balance, we have to move this fulcrum in a way that you have here an L, and you have here 3 to L. L is the length of your lever. The problem goes like this, that a volume of a sphere times 3 of L equals to V of a cylinder times L, which then goes to volume of this cylinder, sorry, with regard to a volume of a sphere is 3, 2. All you need about this is to understand what a volume of a sphere is and what a volume of a cylinder is. Then thinking, even in imagination, how can you balance a lever that has a cylinder on one of its sides, one of its poles, and a sphere on another? The important thing is that in order for this thought experiment to work, you need to give them, both the cylinder and your sphere, substances with the same density, namely the material should be the same. Once you do that, then you are capable of basically moving the fulcrum of the lever in the actual experience or in thought in a way that it corresponds with the volume and the weight of your sphere and cylinder on the two poles of the lever. Once you do that and you make a balance, then you are capable of articulating or elaborating the relation between the cylinder and the sphere that it envelopes. There are so many examples of these basically geometrical reasonings done by actual building of mechanical analogs or done in thought experiments, simply by referring or delegating a problem to a mechanical engineering problem, done in late scholastic and medieval eras. A very, very important example of this is Orim's invention of formula for acceleration that later on becomes a diagram for classical perspective. So when you look into math history books and art books, you always see that invention of classical perspective in painting was due to, for example, the interventions of artists, medieval artists. But that is absolutely not true. Before artists actually came up with the diagram, the actual diagram of classical perspective, it had already been proposed by scholastic philosophers, particularly Orim. He had already, and the interesting, really the interesting point of this, that there is a connection between simple Archimedean machines, formula for mean speed, formula for acceleration, and classical perspective. So you have a dynasty of problems, of geometric and mechanical problems that are put together, allow you to transcend to a higher problem that subsumes or sublate, in a Hegelian sense, your current problems into a higher order geometric problems that consists of both mechanical problems and rudimentary geometric problems. And by virtue of that, you are capable of building higher order mechanical and geometric problems. And classical perspective is one of this. Classical perspective is not pure geometry. It also has, once you start to decompose it, you see that it is really a diagram of uniform acceleration, which can also be seen as a frictionless acceleration on an inclined plane. Inclined plane. Imagine if you inclined plane, the diagram of geometric diagram of an inclined plane, and you had manipulated geometrically in a way that you could expand it, turn it to the perspective operator, then that is basically your diagram or graphical representation of a 3D version of your classical perspective diagram. It's simply an inclined plane that has been basically whose geometric and physical qualities and characteristics have been sublated into an optical problem. So I'm going to talk about this, about basically how can you get a diagram of classical perspective, something like this, from geometric problems and physical problems that have nothing to do from superficial stance, have nothing to do with an optical problem about perspectivality. Before then, it's important to talk a little bit about who Orim is and what exactly his project was. Any question before I move forward? Okay. So let me turn off this now. Okay, can you see me?
Yeah.
Okay, good. So Orim was a student of John Buridan, one of the most famous scholars in Merton College of Oxford. Orim was a famous French archbishop and theologian, economist, and natural philosopher in the Middle Ages, who was the head of a school of Paris. And he did make significant contributions to economy, to banking, to engineering, natural philosophy, theology, and the rise of what you might call to be modern philosophy of knowledge that was completely divorced from the kind of rudimentary relations between science, theology, and magic of Middle Ages. It's also really, if you are interested, you should definitely read his book on money, which is, it's really the first book that starts to elaborate about the abstract powers of monetarization and money as an abstract entity. And it is actually quite astonishing how much his book on money is also connected. His book on forms, abstraction, mathematics, and kind of like his natural philosophical stance toward physics and mathematics in Middle Ages. So but what we need to know is that Orim's contributions are by no means radical, in the sense that he did not simply come up with some of these fundamental insights all by himself. He simply integrated them into revolutionary theses. He was like any other medieval scholastic philosopher, was working in the context of logics, mathematics, theology, a national philosophy of his time. And he was extremely influenced, as I said, by the Merton School of Oxford, the so-called Oxford calculators, but so as medieval Arab or Muslim philosophers, particularly Ibn Sina, Avicenna. And the reason that I'm particularly emphasizing Avicenna's basically philosophy in relation to Orim is that so many historians believe that Avicenna's commentary on the relation between mathematics and physics is essentially the fundament of the entire process of what you might call to be empirical sciences, that he simply articulated in very basic terms a relation between physics and mathematics that paved the road for mathematization of nature, the so-called, what you might call to be the advent of Enlightenment sciences. One of the most important observations about Avicenna's relation between physics and mathematics is the relation between what you might call to be quantities and qualities. Couched in vocabulary of a scholastic philosophy, these can be thought in terms of the relation between the triad of the so-called quantities dimensionalis, quantities virtualis, and formula corporalis. So what are these three entities that constitute the triad that make up the relation or elaborate the relation between physics and mathematics? So quantities dimensionalis, very roughly speaking, is about the kind of quantities, namely degrees of intelligibility. When we are talking about quantity at this point in scholastic philosophy or Middle Ages, we are not talking about literally about what we mean by quantity these days, but it has also a conceptual input. Quantity in Middle Ages is about degrees of intelligibility of nature. So there is a direct connection between the development of the system of quantification in this time and the metaphysics of intelligibility, of those which exist. Now, so quantities dimensionalis tries to, or basically pertains to, the distinguishing features of a body in a space in terms of length, width, and depth. This is called quantities dimensionalis, that allows a body to receive this or that form of determination. Quantities virtualis is a basically different from, fundamentally different from, although even though it's connected to the quantities dimensionalis, it's different from quantities dimensionalis. So what you might call to be the extensible properties of the body. Quantities virtualis are about undetermined or indeterminate qualities of a body in itself, what you might call to be the subjective properties that partakes in one or more qualities, like heat and cold. And these quantities virtualis can be thought in terms of, for example, it's getting cold, this bar of iron is getting cold, this bar of iron is getting hotter. Or, for example, this projectile is moving faster. This projectile is moving slower. Velocity or heat, in this sense, is a quality in which a subject, namely a body, partakes in. And this act of partaking in a specific quality can be also thought in terms of duration of time. Along this duration, the body X partakes in such and such qualities, in such and such degrees. So this is, you can see that quantitas virtualis is connected with the idea of intensibles, namely intensity, in the vocabulary of philosophy. Whereas quantitas dimensionalis are about extensible properties, namely extensional properties of a body or a subject. So in addition to quantitas virtualis and quantitas dimensionalis, we also have formula corporalis. So formula corporalis, you can think about this as the relation between intensive qualities and extensive properties. How intensive qualities give some characteristics to extensive properties, and how extensive properties, namely quantitas dimensionalis, elaborate certain intensive characteristics, namely quantitas virtualis. This is what you might call to be corporal or corporeal form of a body, corpora formula, forma corporalis. So everything in the vocabulary of Middle Ages, and particularly for Avicenna, Avicenna is the first one who actually come up with this triadic way of looking at bodies or subjects. Everything in Middle Ages is laid out in terms of the relations between these three compartments, or three essences of a body or a subject. The relation between the intensive, the extensive, and the corporeal. And the corporeal is simply what you might call to be the, is afforded by the individuating power of intensive and extensive properties. So we essentially have, and the whole idea is that this relational characteristics for any given body are essentially telling us about how we can render this or that body intelligible. So the purpose of laying or characterizing a body in terms of quantitas dimensionalis, quantitas virtualis, and forma corporalis is to come up with a system that allow us to methodically start to think about what bodies are and how they behave intelligibly in terms of intelligible properties. So we see that basically from this perspective, people like Avicenna and Urim lay out the foundation of a modern system of knowledge. It's based on elaborating intelligible properties of an object or an item. And as we see, we already have a triptych, in which we have some extensible properties, like volume. We have some intermediate or virtual properties, and we have some material characteristics, like mass. They're always constant. We can see in this formula something like the virtual characteristics that basically start to fold and envelope variation of extensible properties of a body in space in terms of characteristics of pure material properties as hinges. So you might say that something like virtual characteristics hinge extensible properties and pure intensible properties. They allow us to articulate variations in terms of invariances, or explicate an invariant property, like something like a constancy, like a mass, in terms of variations, like here in this formula, like volume. So for any articulation of anything intelligible in the world, any object, we essentially need not only the extensible properties and the intensible properties, but something that mediates the relation between the two, the so-called hinge, that render this system of intelligibility possible. This hinge are called virtualis, or quantitas virtualis, or virtual quantities, virtual properties. These virtual properties, you might think about them in terms of how some purely intensible properties are being distributed in a space. And how, if you have, for example, the extensible, namely distributed properties of an object, like a projectile in a space, then how can you reconstruct these, extended characteristics, spatial characteristics, namely the quantitas dimensionalis, back into those pure intensible properties? How can you make intelligible the relation between purely intensible and purely extensible? You cannot do that unless you have something like dimensionalis, quantitas virtualis, that you can think about them as hinges between intensible and extensible properties. So before I move forward and elaborate how Orim starts to elaborate this and turn this into a very inventive way of solving the problem of acceleration, is there any question?
So quantitas dimensionalis is extensities.
Extensitive, like completely Spinozian properties, like of a body in a space.
And intensities is quantitas virtualis, is that what you said?
They are, in medieval philosophy, they are associated mostly with pure intensities. They are what you might call to be are ways or relations by which a subject partakes or participates in its qualities. What does that mean? Imagine a bar of iron is a subject. A bar of iron is a subject. You heat it up with flame. How does the subject participate in the quality of being hot? Now, you see, as you heat up this bar of iron, something happens to it. It expands over time. The expansion of the bar of iron are its extensible properties. Its completely intensible, undetermined, generic properties are what you call to be are pure intensities. The way that the ways by which it partakes in the quality of being hot, so as to extend such and such in a space, are quantities virtualis. Quantities virtualis are not given to us. But the difference, what is given to us are extensible properties, because we can see them, how a body expands in space. The pure intensities, for example, something like mass in our formula of m equals to dv, are undetermined. We absolutely don't know what the fuck they are. But we can create between what is given to us and what is completely undetermined by creating a hinge, a system that starts to elaborate how something that is purely intensible can be correlated with something that is purely extensive. These are quantities virtualis. You might call them are basically ways of making an object intelligible in a space by elaborating how forces or kinematics or dynamics are being unfolded and laid out in terms of a spatial extensible properties.
Sounds good. Great for me.
So, by the way, should we have a break, like 5 minutes, and then come back?
That sounds fine. Are people okay with that? I mean, if you don't speak up, I'll assume that's okay.
Okay.
Yeah, that would be great.
Okay.
Okay, superb.
Right.
See you in 5 minutes then.
Sounds good.
Any question before? Daniel, what do you mean by modal, the status of axioms in Hilbert systems? The level of, logical relations between axioms, what you might call to be the micro theoretical relations. At that level, the relations are usually necessary in order for you to have the possibility at the level of macrological theory or macro theory, namely the space of model constructions. They can be intuited or intuitive. Logical relations between intuitive axioms, but they can also be fundamentally abstract axioms. Again, completely put in terms of in formal, non-formal set theoretic terms. The point is that Euclid's axiom is intuitive definitions. Even though it has the intuitive definitions, once you see the relation between the axioms completely in logical set theoretic terms, you can derive different models from your intuitive axioms. But not all axiomatic systems have intuitive axioms, like Euclid. Some have, and this is a Segmuller's and also Lawrence Ponton's point of view, that axioms can be fundamentally abstract, laid out in set theoretic predicate logic terms. So should we start?
Sounds good. Yeah, it's been a little more than 5 minutes. So.
Okay. So as you have already noticed, this triptych of characteristics pertaining to an object, material characteristics, virtual characteristics, and dimensional characteristics corresponding to pure intensities, intensival characteristics, and extensive characteristics, can allow us to think about how we can render any quality whatsoever that we see in the world intelligible in terms of degrees of intelligibility. This is the project of quantification. Quantification, the project of measurement, is the project of articulating degrees of intelligibility for any given quality, no matter how intensive it might be, or how convoluted it might be, like trepidation, heat and cold, like motion in motion. You know, motion from a scholastic perspective is a quality from Aristotelian metaphoric sense. But sometimes we don't have just one motion for a projectile. We have sometimes motion in motion. Isn't it the whole idea of non-uniform acceleration, motion in motion? So if this is the kind of convoluted quality that an object has, how can we render this intelligible? How can we quantify it? This is the project that essentially lays the groundwork for the advent of the Copernican revolution. And the person who takes this very seriously and makes the most significant contributions is Nicole Borin. And in fact, majority of historians, as I said, think that Galileo and Copernicus equations of motion with regard to celestial bodies were completely derivative with regard to Borin's diagrams, Borin's system of graphical geometrical system of studying the motion and velocity of bodies. In a sense, Copernican revolution wasn't a radical breakthrough, but simply a modification of what is already available in the scholastic philosophy. So, let me turn on the So, or even start to think about the relation between quantity and quality in terms of Avicenna's triptych of pure intensity, intensible and extensible properties that I mentioned. We know that velocity is something like delta x divided by over delta t. Change of distance with regard to change of time. Now, from a modern perspective, we might see this to be representing a graph This is your x distance. In which you can build a vertical line representing the distance, L or x, and a horizontal line representing a t. And then saying that the line, the diagonal line, this one, the hinge between your vertical and horizontal is L equals to Vt. And then basically every part, every instance or every moment of your motion for a given projectile simply will be articulated by a bit of y-axis and a bit of x-axis, a bit of distance and a bit of time. This is, from a modern perspective of a graph, this is completely fine. But Orim did not go for this solution. And in fact, as I will argue, Orim's solution was much more non-trivial and advanced than the modern graphical representation. Simply by virtue of understanding of what it means for this hinge, for this graph, to connect the vertical and the horizontal. The extensible properties and the intensible qualities expressed in terms of duration or time. By creating a device or a diagram that could fold durable or durational intensive properties and unfold them in terms of extensible properties, or the other way around, enveloping extensible properties back to the purely intensive properties, or unfolding intensive properties in terms of extensible properties that we can measure, that we can quantify. This hinge, this diagrammatic hinge that didn't see the idea of intelligibility of a body in a space no longer in terms of simply coordinates of y-axis and x-axis, purely intensible and purely extensible properties, but only as a breadth or amplitude, and hence the word amplitude, amplitude of degrees that are capable of folding and unfolding, going back and forth, degree by degree, between extensible and intensible properties is the very idea of quantification. And Orim's had a significant emphasis in how this idea of amplitude, the hinge between extensible and intensible, can be expressed in terms of diagrammatic representations, laid out in analytic geometric terms that can be traced and elaborated by way of Euclid's system. Now, let's see how this works. First, a rudimentary example that I already mentioned. Imagine you have a bar of iron. which you are heating. So the quality that the subject, called a bar of iron, is partaking in is heat or hotness. How are you going to render the idea of hot or heat or being hot for this bar of iron intelligible? This is essentially the idea of quantifying the degree of heat within a single subject. Here, the bar of iron. So, understand this. As you are heating this bar of iron, the bar of iron is going to expand. What is the expansion of the bar of iron?
Extensity.
Yes. Oops, sorry. So, So first, at time t1, it expands this amount. T1, let's say, to T2. T2 to T3, it expands this amount. And T3 to T4, it expands this amount. Expansion of a bar of iron are the extensible properties of the body that can be laid out in terms of quantities, dimensionals, length, depth, and width. What you might call to be the formal properties in today's physics sense. It's a spatial properties. Now, if we have this, so this bar of iron is participating in a quality, which is heat, being hot. By virtue of participating in this quality, it exhibits some extensional properties, namely expansion in the space, according to some duration or time. Now, if we have this expansion, namely the bar of iron expanding from time to time, how can we say or elaborate the precise degree by which this bar of iron has participated in its own quality, in being hot? The project of quantification. Come up with a diagram that can accurately represent not only the expansion of the bar of iron, but its participation in the quality of being hot. Any idea?
So the example that Ari did not use is the time as the x-axis and expansion as the y-axis.
Yes, yes. So basically, the y-axis, what you might call to be the intensible at a specific time. The intensity at a specific time, the quality at a specific time. This is what Orim calls latitude of form. Forms in medieval vocabulary are simply synonymous to qualities. Forms, wherever you see form in medieval text, is simply quality. So Orims call these vertical axis, corresponding to the y-axis in modern sense, latitudes of forms, namely the intensity of a quality at a given time. He calls the x-axis longitude. Longitude are what you might call to be the subject's participation, the subject duration of participating in its quality. Now, from this perspective, x-axis does not represent extensible properties, but purely intensible properties. Participation in its own quality. Like a bar of iron. So we have something like this. At time T1 to T2, the bar of iron grows this amount. At T2 to T3, the bar of iron grows this amount. T2 to T3. And finally, oops. The bar of iron grows this amount. If you see the time vector or the durational vector, which corresponds to your x-axis, is simply a register of the durational characteristics of the subject participating in its own quality, pure intentional or intensible properties. Basically, so this is the longitude. This is the latitude. The latitudes are the one that you can say are more in tandem with what you might call to be extensible properties. But that's not purely correct, because latitudes, so you had this in the modern version is something like this. So you have a line and you have x, y axis, and then any point of your line has a bit of x-axis and a bit of y-axis. But here is a different thing. Your latitudes are not being diagrammed or represented simply in terms of lines, but in terms of areas. Namely, how much extensive properties unfold durational properties. As you see, the area here of each of these rectangles represents the amount or the degree of the quality expressed in durational properties. This is the idea that in a scholastic philosophy they call it amplitude. In modern terms, we call it amplitude, the breadth, the width. So the amplitudes, you might see them not simply in terms of extensible, intensible properties alone, but in terms of how they envelope, how extensive properties develop intensible properties, and how intensible properties envelope extensible properties. This is the idea of amplitude, the breadth. The idea of a hinge.
Breadth is essentially just the amount of change that the subject undergoes when it's exposed to the flame or the variable.
Yes, yes, which can be, if you represent it in terms of area, rather than a precise coordinate that has some bits of x and y axis. If you represent it as an area, then you can represent it in terms of degrees of folding and unfolding between intensible and extensible. Exactly like the formula M d V. D is density, V is volumetric, extensible properties, completely variational. N is invariant, constant. D is something that hinges and ontologically precedent M and ontologically consequent variational term called V, volumetric variations. It does not simply, like the modern graph, is something that has a bit of this, a bit of that. But you can think about this D, this hinge, which here in Orim's diagram is expressed in terms of the area of a rectangle, as something that captures how much degree of the variation can be attached to something that invariance, and what it means for this constant property or quality of form or invariance at this time, for this duration of time, to be unpacked, decompressed, or unfolded in terms of such and such extensible properties. Any question?
Can you think of an example that's not using area, or is area?
Oh, area is absolutely necessary for
Okay.
Orim. Area is basically the whole idea of elaborating the relation between pure intensible and pure extensible, not in terms of some pure determination, but in terms of unfoldings, in terms of degrees of intelligibility. Degrees of intelligibility is the very idea of quantification and measurement. It is not arbitrary. It's a matter of determination. And determination is not something that is given, but it's a matter of procedure.
So, but could we use something like, instead of using area, could you use weight or mass? Or
Area is simply a graphical representation of these things.
I see. Okay. Yeah.
So he wants to come up with a universal graphical representation of elaborating this hinge, density, or for example, velocity, acceleration, so on and so forth. A hinge between time and space, between durational properties and purely extensible properties. And you see the relation here that I mentioned, that construction of new spatial invariances has something to do with our idea of what is intelligible in the world. First few sessions we were talking about gestures and construction of spatial invariances, and this is it. The construction of spatial invariances that are capable of connecting between durational properties of a matter and extensional properties of a body are absolutely connected to what we know as making something intelligible. Without this hinge, without these intermediating spatial constructs, here represented by an area in Orim's diagram, we couldn't have something like an intelligible object. So let's
something that just occurred to me is like maybe like the intensible qualities and like the extensible qualities are like the relationship is like the relationship between the first and the second line in the Plato metaphor, because it's all about how how we can comprehend intensive qualities through the what structures of intelligibility we need in order to constitute at the second line as a understood constituted objectivity. Oh no, he left.
Yeah, I think we just lost him. We'll just wait for him to come back. Can you expand on your point, Christian? What do you?
Well, I was just thinking, because I mean, it seems to me, or like not necessarily, I don't know, because it's like the universal conditions to express tensive qualities as extensible. So I mean, I'm just trying to put it into terms of the four-line metaphor in Plato.
Right.
Because like, I mean, on one hand, like it seems like the intensive side is definitely.
Sorry, I got kicked out. Okay.
Oh, basically, I was just asking like how this fits in with the four-line metaphor in Plato. Like, because I mean, it seems to me like the intensible side would be like the first line with the indeterminate qualities, but in order for them to be fully expressed, you'd need some structure of intelligibility to constitute the objectivity as such.
Well, the whole idea is that these so-called hinges, quantitas virtualis, are really the whole idea of mathematics. In the divided line, they refer precisely not to the epistemological, but the metaphysical status of mathematical or analytic idealities in the divided line, namely the third segment, being posited between pure idealities and so-called objects in nature, allow you to bridge between multiplicities of objects in the world, variations and extensible properties, and invariances that are given by the metaphysical status of pure ideal realities. Forms in Plato have reality, and that's why so many people believe that Plato's ontology is a two-level ontology. Objects have their own reality, ontology, but that reality is ultimately dependent on the reality of forms. Which are one, which don't have any multiplicity. So how much time do we have, by the way?
So we're at 3:20 right now, so we have about 10 minutes.
Okay, so just I think that we will go next session, and I will talk more about details about Fourier diagrams. Well, very briefly, to wrap up today's discussion in terms of what we were talking about. So, what is interesting in Fourier's formulation of Avicenna's principle of triadic entities of any intelligible system is that precisely because the mediating term, namely quantitas virtualis, is graphically represented in terms of an amplitude, an area that envelopes some degrees of variations. It already suggests or speaks of this fact that precisely because graphical representations or the third medium, the intermediating medium, the so-called quantitas virtualis, enfolds variational degrees. Depending on how we can graphically represent or geometrically pose this amplitude or this intermediating term, we can come up with new intelligible properties with regard to an object. So within the metaphysical status of Fourier's diagram, we can already anticipate that if, for example, if we graphically represent quantitas virtualis as an area that envelopes some variations, we can elaborate or we can demonstrate, come up with some intelligible properties about a body that participates in equality and exhibits such and such extensive qualities. But it also means that precisely because it's a graphical representation, the envelopment of variations could be thought not in terms of simple Euclidean area, but in terms of other geometrical entities. Which means that if we have, and this is more in line with the metaphysical epistemological status of Avicenna's and Fourier's diagrams, that if we had a different geometric entity that could express this envelopment of degrees in a different geometric form rather than simply a Euclidean area, then we could make explicit further intelligible properties about an object. And this is exactly what you see in post-Galilean Copernican relation between physics and mathematics, where mathematical models, particularly geometrical models, give us more intelligible properties about the behavior, the extensible behavior of an object in a space and time. Another interesting point about Orim's diagrams is that, if you have already noticed, we have some pure intensity, we have some pure extensity, and we have some amplitude, some breadth, some degrees of folding and unfolding between them. This plasticity, this intermediating plasticity that is between elasticity and pure extension, between intensive elasticity and pure extension, can be thought also dynamically in terms of what it means, what is exactly the mechanical function of this plasticity. How can we diagrammatically represent it? How can we think about this plasticity or amplitude that is capable of intermediating between pure intensible properties and pure extensible properties, but without being reduced to either one of them? As I will talk about in the next session, this is essentially the idea behind Orim's diagrams of a mean speed and uniform acceleration, in the sense that what we are dealing here, you can think about the amplitude, namely these intermediating entity, in terms of some sort of process of contraction and decontraction. Something that contracts extensible properties to intensible properties and decontracts intensible properties to extensible properties. A good diagram of this, by what I mean, and of course I will talk about how this is related to the formula of mean speed and acceleration, will be something like this. That you have Can you see the whiteboard?
Yeah.
Okay, so if you remember, you had L and you had T, or you had X and Y axis. One was vertical and one was horizontal. The amplitude is not something like this, the modern graphical representation. The amplitude is something like this. Think about this in terms of a machine, a mechanical engineering problem. If you were going, this is degree 1 of velocity or intensity, and this is degree 0 of intensity. Between 1 and 0, there is a continuum of degrees or variations exhibited by the so-called amplum or amplitude or the hinge, quantitas virtualis. Now, quantities virtualis, you can think about it as this series of hinges and joints that you can compress it or decompress it. Like if you had one of these joints, I'm sure that you have seen this, these hangers that fold and unfold. And this is exactly like that. That the amplum represents a continuum of degrees that you can, according to the principle of how you articulate the relation between your extensible properties and extensible properties, unfold it and fold it. Between 1 and 0, there is an infinite continuum of degrees.
So this is not like a seismograph where it...
No.
No. Okay.
No. Yes. This enfolding and unfolding degrees, as I mentioned, Orin represents them by way of area. Area formulated in the Euclidean system. What is area exactly? Area is L of a rectangle, L, and its length and width. How they can be connected to one another can be expressed as the area. You can express this, how L and T, 1 and 0, length and width can be connected in different schemas rather than just area, depending on the kind of geometric system or mathematical structure you are using. So you can essentially have different classes of intelligibility between an object participating in its qualities and its extensible, extensional properties, its behavior in space and time.
So I'm sorry, I don't understand the zigzag type graph yet, or what it's measuring or how it's measuring.
The zigzag measuring is simply what you might call to be the mechanical diagrammatic understanding of how 1 and 0, length and width, or for example, length and time, distance and time, are going to be translated to one another. Basically, how they can be translated to another by creating different continuums, amplitudes of degrees. And how can you express these amplitudes can be numerous. But simply all you need is a mechanism for compression and decompression. Here, we are just coming with a rudimentary idea of compression and decompression. It's like the idea of a joint system in mechanical engineering. You create joints, then if you compress it, it will become a vertical line. If you decompress it, it becomes a horizontal line.
Okay, yeah, I understand that now.
We will talk about this, how Orin really implements this to come up with his idea of mean speed and the formula for uniform acceleration, allowing him to understand what is exactly the nature of motion in motion. Because in Aristotelian metaphysics, you don't have motion in motion, you only have a motion. In fact, motion is a contradictory term, but you can have motion in motion. This is the very idea of acceleration. If you have a motion in motion, then you are capable of talking about various rates of motion among celestial bodies that cannot be commensurable. And hence, you can think about cosmos differently. And that's why, basically, Orim is extremely important from a historical perspective in giving rise to the Copernican and Keplerian revolution. Again, as I said, motions are quality. Velocity is a quality from a scholastic perspective. A body that participates in motion is a subject that participates in a specific quality. The quality is not given to us. We need to render it intelligible. Namely, understand or elaborate the relation between the position and time of a projectile at time x1, t1, and its intensible properties, but also capable of not simply talking about these positions in discrete time and space, but in regard to one another as a configurations. And this is the idea of amplum. Amplum, you see, in old diagrams, in modern diagrams, we had this, that for example, time x1, time x2, t2, you see, we have this as disjointed instances of projectile moving at uniform acceleration that can be, at each instant, can be expressed by a bit of time x-axis and a bit of y-axis. But what Orim's manages to do is capable of configuring and showing the relations between each of these instances of the projectile at time x1, t1 with regard to time x2, t2 with regard to time x3, t3 ad infinitum. So he's capable of intuiting the motion of a body in a single coherent intuition. Not as disjointed degrees, but simply every motion with regard to the previous motion. Precisely because you have this comparative analogical system now, then you are capable of also thinking not about uniform motion, but also non-uniform, what Orim calls difformly uniform motion, non-uniform acceleration. A motion of projectile that's at time t3, in terms of time and position, is fundamentally different from its previous motion at time t2 and x2. So you have non-uniform acceleration. So you have the idea of motion in motion, precisely because you were capable of moving from this disjointed view of qualities, the relation between intensible and extensible, to the amplitudinal view of how extensible and intensibles are related. Not disjointedly, but in terms of degrees of variations. And then you see that basically this, ultimately, this understanding, if you don't have this understanding, you never had anything like the idea of acceleration. Acceleration would be impossible for you to think about. Because acceleration essentially requires degrees of variation between intensible and the extensible. Degrees that can be quite also non-uniform. And if you didn't have accelerations, you couldn't have equations for the motion of celestial bodies. If you didn't have those equations, you couldn't have anything, something like Copernican revolution or Keplerian revolution or Newtonian revolution.
So is the rendering intelligible about the dimension of an object, like a single sort of variable, or is it claiming like a being of the object itself?
The intelligibility is not, as I mentioned, is not about the extensible versus the intensible or intensible versus the extensive. It's about how we can bridge the dimensions to qualities, quantities to qualities, extensible quantities to intensible qualities.
So is there a degree of full intelligibility?
I think from this, at least from a metaphysical perspective, the degree of full intelligibility is erroneous. Precisely because, from at least the scholastic perspective of metaphysics, matter, precisely because of its potentialities, can be expressed differently in terms of extensible quantities. And if you are, and precisely because of this, then there are infinite ways of making this matter and its extensive properties intelligible. Given the fact that the potentialities of matter, at least in the scholastic philosophies, are infinite, its extensible, its intelligibilities are also infinite. So from, at least from a scholastic perspective, there is no exhaustive form of intelligibility. In fact, the idea of intelligibility from a scholastic perspective points to the inexhaustibility of what matter is. Remember, in the formula MdV, M is the one that has ontological precedence. D is the intermediating term, and V is the variational or extensible term. M is on the other side of the formula. Precisely, this shows this ontological precedence. That D, no matter how much you build it, given the ontological precedence of M, there are infinite ways for increasing the intelligibility without ever exhausting the pure intelligibility of M as such. Any questions? Philip has been silent today.
Yeah, I don't have any questions. You know, I was just watching the up and down variation as thinking of the sine or cosine wave going from 0 to 1 to 0 to 1. Was my only.
Yes. No, it is actually quite interesting to see that even the graphical representation that Urim offers, you can see it in every basically avenue of mathematical physics these days. That is simply the idea of mathematical physics, the relations between mathematics and physics, mathematical structures and physical properties, particularly in terms of motion, namely extensible properties. The only reason I will talk next session, the only reason that Urim's couldn't come up with something like full-fledged Copernican revolution was because he did not have something. First of all, most important thing is that he didn't know the implications of his own diagrams. he had built these sophisticated geometric systems for representing the relation between qualities and quantities, but he didn't know exactly the implications of his own diagrams. One, but also second, is because of his, precisely because, you know, at this time we don't have anything like differential calculus. All he had was analytic geometry, namely Euclidean system. He could not have something like limit functions that allow him to represent these diagrams in terms of curves, current modern understanding of a graph. Hence, he couldn't really understand what it means for something to have a form of motion that is deformed, namely non-uniform acceleration, instantaneous rate of change, that allow you to think about various motions with regard to one another. These are all, of course, analytic geometry already gives you a very, very approximate, precise, approximate way of understanding what a curve of a graph can be. This is the exhaustive method, again, invented by Archimedes. You can, in fact, calculate the area underneath a curve by way of rectangles, by creating ever smaller rectangles under the curve. This is a method of approximation. But nevertheless, it is not really give you a way of understanding what the curve itself is. That had to wait for the invention of modern calculus, particularly the introduction of limit function by Weierstrass. Okay, questions before we end today's session?
Well, there are all sorts of prefigurations of the calculus, right? The limits of exhaustion by Eudoxus and so forth, of kind of filling out circles with
Squares.
Squares and hexagons and triangles.
Yes, absolutely, yes. Method of exhaustion is quite actually
I mean, it's integration. It's a form of it, anyway.
Yeah, absolutely. I will talk about this. How the Orim's diagrams actually a method of integration. Next, very quickly, you see, the whole idea is that, for example, think about our bar of iron, that, for example, in each time period, it expands such and such amount. So you have some X and Y axis, and you have, for example, this expansion at this time, you have this expansion at this time, and then you have this expansion this time, this expansion at this time. Now, of course, you can create something like curve, or of course, he didn't have that. So he was trying to think about uniform expansion of a bar of iron, which you can easily connect the head of these triangles by a line. This line, he called it the line of summation. The line of summation is absolutely the idea of an integral.
Right, and the other thing I was thinking about, I mean, just free associating, is of course, we read it as we read the dimension of time as a form of becoming, but that particular mode of reading what we were doing with the methods of exhaustion in classical times, and maybe what I'm doing here is channeling a little bit of Spengler's notion of incompatible number worlds or math worlds, which I was just glancing at for some reason yesterday. it can never see what it's doing in classical times as the unfolding of a time dimension, right?
Yes, yeah, no, absolutely, yes. I mean, this idea of becoming, I think, in fact, is a little bit misleading when we start to think about the relation between intensible and extensible. Yeah. Even putting modern physics is very misleading. In modern physics, essentially, it has changed, but without the idea of metaphysical becoming or durational properties. And this is exactly what every change can be expressed in terms of metricization of the spatial properties.
Right. Quantum entanglement, yeah.
I mean, basically anything that you have in quantum mechanics, in modern physics, is really metricization of the space. You can all, forego with the idea of durational time or becoming.
I was just going to ask why, or actually, you're still screen sharing if you want to.
Am I?
Yeah. But Philip? Why are you saying that it's a measurement of becoming instead of?
Whoops! Something happened here.
That looks crazy. That's better. Oh nope, it's doing it again.
Okay, go on.
What I was just saying is, from differentiation and the calculus and its use in differential occasions to measure variations in population over time or so forth, that the sort of mainstream of I guess thought about what calculus was doing was it was enabled to represent becoming or unfolding over time. But I think Reza's point is right, is that once you get to quantum entanglement where you can't really locate, or things can be in several places, you can't really talk about a smooth unfolding becoming,
right,
for each particle.
You see, Theodore, it goes like this. What is really, I mean, essentially, the basic idea of differential calculus is instantaneous rate of change, namely, the rate of change between two rate of changes. Now, for each of these rate of changes, you can lay them down in terms of, for example, the relation between extensible properties and durational properties. But if you are trying to study the instantaneous rate of change, the relation between rates of change, then you can factor out the durational properties precisely because they share these durational properties, and simply talk about these rates of change in terms of extensional properties.
Right, I see. I have nothing to add right now.
Okay, thanks everyone. Next session, I will continue with our ORAIN thing, and then I will go to, after that I will also share a couple of texts, old manuscripts. I will talk about the invention of algebra and a geometrical study of quadratic equations.
Should we read for next week?
Oh, I have put a couple of books already in the Google Drive. One is the I will add some more. I will try to put Nicole Orim's manuscript, but I have already added this book called Engines of Imaginations, which is about the advent of mechanical engineering and its relation with geometrical problems in Middle Ages.
Okay, great.
Great, thanks, Reza.
Absolutely.
One question.
Sure.
So, I don't know mathematics too well yet, but like, I know the whole idea of spatial invariances has been really important, and I agree, I totally agree with that. I was wondering if, like, for example, like the intuitions that build the intuitive steps necessary to understand non-Euclidean geometry, would they be built in Euclidean geometry? Like, what? Like, it seems to me like the whole spatial invariance side is really important. So it seems to me if you're understanding space without a scalar invariance, you would need to have a separate space with a scalar invariant in order to do calculations in such an abnormal space.
You see, I think the answer to this is a little bit difficult. Euclidean geometry, yeah, I mean, when you are, for example, thinking about non-Euclidean geometry, and Euclidean geometry, it can be expressed in the terms that you were talking about. But in all of the higher order geometries, the concept of a space is not an intuitive concept of a space. It is, in fact, what you might call to be so when you have, for example, any theoretical systems, you usually have different variations of key elemental concepts. Some of these elemental concepts stand into one-to-one relationships with your axiomatic terms. This is the case with Euclidean axioms and Euclidean systems. But sometimes the concept of a space is not about your axiomatic term, but about the coherency, the logical coherency and consistency, which is abstract, between your intuitive definitions. And in majority of the higher order geometries, the concept of a space is not really about the intuitive components of your definitions, but about the inferential coherence of how these axioms, how these definitions hang together in a logical space. That logical space is what defines the concept of a space for you, rather than simply being traceable to your intuitive components like Euclidean space. So I think from this perspective, it's kind of difficult to talk about the concept of a space in higher geometries with regard to the concept of a space in Euclidean geometry, in which the concept of a space is in a one-to-one relationship with the intuitive perceptual components of your definitions.
All right. Yeah, I was just kind of wondering if you would need like Euclidean intuitions to bootstrap it, but I guess not.
What you have to bootstrap is logical relations. That's exactly what Hilbert's trying to say. That even that you have fixed intuitive axioms, by virtue of establishing logical abstract connections, couched in theoretic terms, between your intuitive axioms, you can create different mathematical models from the same basic axiomatic systems, which might have their own different concepts of space.
Yeah, two comments, Christian. One on your notion of invariance and transformation. There's a whole kind of ladder of geometries of different generalities, even before you get to non-Euclidean geometry, where you're trying to figure out what remains invariant under transformations. And in Euclidean geometry, the transformations are things like rotations, translations, or reflections. And then those have to be distance preserving in Euclidean geometry, and that's called metric space. But then you have all these other geometries like affine geometry, projective geometry, and similarity geometry, where up to topology, where less and less remains invariant. When you finally get to topology, the only thing that remains invariant is the kind of the description of a neighborhood that points are into. So you can think of that as either going down from topology all the way to Euclidean space as a very, very particular and very specified form of geometry as opposed to a more general geometry. The other thing is when you're going into non-Euclidean spaces, or even, I think as Reza said, there's a point after you get from 3 space, you know, 2 spaces the plane, 3 spaces you know, the space we sort of intuit. When you go to spaces 4, 5, and n, you switch essentially from geometry to algebra, because you can't literally visualize these places or intuit them. So you have to describe them by means of numbers, or, you know, differential geometries if you're doing changing curves and stuff.
Thanks very much, Philip.
Appreciate that.
Okay. Thanks, everyone.
All right. See you all next week.
Absolutely.
Thanks. See you
Take
next
care.
Right.
Take care. Have a great day.
Take care,
Bye-bye. Bye-bye.